Hey there, it's Shannon Magic Myers coming at you live from San Diego, California, yet again. All right, today we're going to take a look at two classical theorems, and we will also be showing the uniqueness portion of the quotient remainder theorem. So, are you ready? Let's get going. Two very famous theorems in math are that the square root of 2 is irrational and that there are infinitely many prime numbers. We'll also check out the proof that Q and R from the quotient remainder theorem are unique, like I was saying. So, Greek mathematicians believed that given any two line segments, call them A and B, they don't have to be the same length, a certain unit of length could be found so that the segment A was exactly A units long and segment B was exactly B units long. The segments were said to be commensurable. With respect to this special unit of length. Then the ratio of lengths A and B would be in the same proportion as the ratio of the integers. Note that they were into whole numbers because these are lengths. So these integers A and B would be in the same proportion to the ratio of the lengths, okay? So of those two segments. So here, just writing it in some other notation, what they were saying is that, hey, the length for A, segment A, right, over the length of segment B would be in proportion to these integers A over B. If you look at this square, it's fairly easy, right, to be able to find the square root of 2. If you let each side be of length 1, then this diagonal will be what? Remember that c squared, if we call this c, is equal to a squared plus b squared. So you'd have 1 squared is 1. So you'd have c squared, is equal to 2. Thus, c would equal to the positive square root of 2, since it is representing a length. If the belief of these ancient Greeks was correct, there would exist integers A and B such that the length of the diagonal, right, over the length of a side, remember they're all of equal length since it's a square, would equal to A over B. And this implies that C, so substituting in length of the diagonal over the length of one of the sides, we'll just continue calling it B, would equal to the square root of 2 over 1, which is root 2, and that would be equal to A over B. But if that were true, what would happen? The square root of 2 would be rational. Well, in the 4th or 5th century BCE, the followers of Pythagoras they had like, it was kind of like a cult. It was a religious sect almost. And so these followers of Pythagoras discovered that the square root of 2 was not rational. And it was devastating to them because they like really, really believed in the power of whole numbers to describe phenomena, right? So since this ratio, right, for the diagonal of a square was not rational, they had to readjust their whole way of thinking. So don't be resistant to change. You might go crazy. All right, so let's take a look at Theorem 4.7.1, which is the square root of 2 is irrational. Okay, so we're going to prove this by contradiction, right? So proof by contradiction, just so you know our evil plan. So the negation of this statement is pretty easy, right? Suppose the square root of 2 is rational. Well, and this is something that you need to just know by heart. What does it mean for some number to be rational? There needs to exist. Beautiful. Some, I don't know, whatever you want to call them, A and B, that belong to the integers. We're going to add something special in. We're going to say with no common factors. And also remember B can't be 0. Such that, well, the square root of 2 would equal to A over B, right? By definition of a rational number. And so if I square both sides, what would happen? I would get 2 is equal to A over B, the quantity squared. And we'd have 2 is A squared over B squared. And so A squared would be what? Beautiful, 2B squared, using some algebra. Now, remember that B squared would be an integer, right? Because of closure. The set of integers, if you multiply 2 integers, you get another integer, right? So it's also an even integer, right? And so here, the fact that it's an integer, the even part comes first. So that's by definition of even, right, which we've proved before. And the set of integers is closed under multiplication. All right. So, okay. Let's think about A, right? So if you recall from before, it was in the last section, we proved a proposition numbered 4.6.4, and that proposition said that if the square of an integer is even, then the integer itself is even. So we're going to utilize that, all right? So based on what we have here, right, what can we say? We can say there exists some k that belongs to the integers such that a is equal to 2k. So I'm just replacing the b squared part with k. Well, let's take a look at what's going on with this. We've got A is 2k, right? So if we square both sides, we get A squared is equal to 2k, the quantity squared, right? And what? Good. A squared would be 4k squared. And what did we have for a squared before? We had a squared was also equal to 2b squared, right? So by substitution, couldn't we say that 2b squared was equal to 4k squared? And then isolating b squared, do you see we would get 2k squared? And 2k squared is an even integer. For the same reasoning we had before. So B is even. And this is where we're going to utilize that one theorem. Or was it a proposition? Proposition 4.6.4. Right? Where if the square of an integer is even, the integer itself is even. And what does that mean? Well, this means that A and B have a common factor of 2, right? If they're both even. This contradicts our supposition, right? So, therefore, the square root of 2 is irrational. Remember, with a proof by contradiction, once you get your contradiction after assuming the negation of the conclusion, not the premise, then you are done. You're good to go. And I just wanted to clarify here, when we said A was equal to 2k, this was also by proposition 4.6.4 from the text. Cool? Okay, so moving right along, we have to do some preparatory work in order to get to the theorem about the number of primes is infinite, or there are an infinite number of primes. So here, proposition 4.7.3 says for any integer a and any prime number p, if p divides a, then p does not divide a plus 1. All right? So again, we'll do a proof by contradiction. Why don't we start out by letting p be any prime number. And a belong to the set of integers, right? Because that's given in our premise right here, right? So, suppose we have an if-then statement, right? So how do you negate an if-then statement? Awesome. You got to use De Morgan's laws. So the negation of if P divides A, then P does not divide A plus 1 would be, suppose, what? There exists some R and S that belong to the integers, right? Such that A is equal to P times R and A plus 1 is equal to P times S. So what we're doing here is we're using the definition of divisibility. And so what we are supposing using De Morgan's laws, divisibility, is that P divides A and P divides quantity A plus 1. So, all right, what are we going to have? 1 is going to equal to A plus 1, that quantity, minus A, right? Because A is any integer. And so if you add 1 to A and then take away A, you get 1. But if you substitute in, what do we have? We would have A plus 1, we supposed was P times S, and A we supposed was P times R, which in turn is P times S minus R, using some algebra. Well, S minus R belongs to the integers under closure. So P would have to divide 1. Why? This here is saying that 1 is a multiple of P, right? Cool. So P must divide 1. But remember, the only integers, and we prove this, the only integers which divide 1 are what? Beautiful. 1 and -1. That was, by the way, Theorem 4.3.2. Also, P is greater than 1. And why is P greater than 1? Because P is prime, right? So that's by definition prime. Okay. So what is this saying? This is saying that P is greater than 1, and it's also saying that P is less than or equal to 1, which is definitely a contradiction. So we've proved this proposition. And we're good to go. Cool? Okay, so next up, let's examine, I just put this theorem out there again. We didn't actually prove it, but I had told you that the proof was in the text, okay? So any integer n that's greater than 1 is divisible by a prime number. Okay? So we're going to use these two things here, this proposition and theorem, to prove this next theorem. And that this next theorem says that the set of prime numbers is infinite. All right? So we'll do a proof by contradiction. And what's our contradiction? What do you think? Suppose it's not, right? So suppose the set of prime numbers is finite, not infinite, right? Well, if that's true, then there exists a prime number, call it P if you want, such that P is the largest prime number. So if we look in ascending order, let's go ahead and list them, right? So what would we have? We would have 2, 3, 5, 7, etc., right? And you'd go on until, and let n, capital N, be the product of all these primes. Plus 1. Plus 1. Okay? So what's that going to look like? N would equal to 2 times 3 times 5 times 7 times P, and then plus 1. Cool so far? Well, what do we know about N? We know that N is greater than 1 because you've added 1 to a positive product, right? And what else do we know? We know that N is divisible by some prime number Q. And that is from Theorem 4.3.4, right? So, okay. Since Q is prime, what must be true? Q must be something in that list, right? We'll just say must equal one of 2, 3, 5, 7, dot, 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 all the way down to P, right? It's got to be in that list somewhere, right? Well, if that's true, then what? Q has to divide that product, right? And does not divide N, which is a contradiction. And so we're done. We found our contradiction, right? So we've shown that the set of prime numbers is infinite. Cool, cool? All right, so now we'll wrap it up by doing the uniqueness portion of the quotient remainder theorem. All right, so recall, given any integer n and positive integer d, there exists unique integers q and r such that n equals dq plus r and 0 is less than or equal to r, which in turn is less than d. Okay? So let's do it. Proof. So the evil plan here is to let A equal to dq1 plus r1 and let A also equal to dq2 plus r2. We're saying, hey, maybe it's not unique, right? Well, we got to say, what number set all these things belong to, right? So actually it would be such that A, D, Q1, Q2, R1, and R2 all belong to the integers, okay? And 0 would be less than or equal to R1, which is less than D, and 0 would be less than or equal to R2, which would be less than D. And that's all from what? The quotient remainder theorem, all right? So if A equals these two different quantities, can't we set them equal to each other? So what we'll do is we will say that dq1 plus r1 is equal to dq2 plus r2. Now the evil plan here is going to be, we need to show that q1 equals q2, and we need to show that r1 equals r2. And therefore, q and r are these unique integers. All right, so what can we do? If we get the r's on one side and the other stuff on the other side, we would have dq1 minus dq2 is equal to r2 minus r1. And factoring out of d, we would have remaining q1 minus q2. And then on the other side, we'll have r2 minus r1. All right. Well, what does this tell us? This tells us that D divides R2 minus R1, right? Since Q1 minus Q2 is an integer under closure. And so what this is saying is what? R2 minus R1 is a multiple of D, right? Okay, let's work with the inequalities now. So we know that 0 is less than or equal to R1, which is less than D. If we multiply each side by -1, we'd still have 0, but then it would be greater than or equal to negative R1, which in turn would be greater than negative D. So rewriting it, what would we have? We would have negative D is less than negative R1, which is less than or equal to 0. Now, if we add to this result, let's add to this result the other inequality, which was 0 is less than or equal to R2, which in turn is less than D. And when we do that, what will we have? We'll have negative D. It's got to be less than R2 minus R1, and that's got to be less than D. Okay? I mean, this is saying what? This is saying that R2 minus R1 lies between negative D and D because D is not equal to 0, right? That's why I didn't bother with the or equal to. R2 minus R1, we'll just write down what I just said, okay? Lies between negative D and D, and R2 minus R1 is what? What did we say about that? We said that it is a multiple of D, right? And so what would that imply? That would imply that R2 minus R1 would have to equal 0. Cool so far? All right. So, coming back to what we're starting with, dq1 plus r1 is equal to dq2 plus r2. Now, this, by the way, above here, let's add one more thing. What does that mean? That means that r2 equals r1, right? So by substitution, dq1 plus R2 would equal to dQ2 plus R2, subtracting R2 from both sides, we'd get dQ1 is equal to dQ2. We know that D is not equal to 0 from our premise, right? So we can divide by D. Therefore, Q1 equals Q2. So we've shown that R2 is equal to R1, and we've shown that Q1 is Q2, and we're done. So we're done. That's all we needed to show. Cool, cool? So the rest of that proof for that theorem will be in chapter 5, and guess what? That's all for this section. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe.